Hey all, welcome to Homeschool and welcome back to Class 11 Chemistry series. We have completed first two chapters in Class 11, that is basic concepts of chemistry as well as structure of atom in a detailed way. All concepts are covered in a detailed way. Say concept clarity is very important to attend the competitive questions of any exam. It may be NEET, JEE or whatever it is. Let me finish all the chapters and their concepts in detail, and after that I will come up with the objective questions on important topics. Okay. See, today I am with the third chapter, that is classification of elements and the periodicity in properties. Okay, so this is nothing but we are learning entire things about the periodic table. Okay, so it's a very fundamental chapter. It's very much essential to understand each and every concept of this chapter, because this will help you to deal with every other chapter that is there in class 11 and class 12 chemistry. So it's very important to understand. You may not get too many questions from this chapter for competitive exams, but understanding the concepts of this chapter will definitely help you in understanding other chapters in a better way. Okay, so try to understand every concept of this chapter. I'll be explaining you all in detail. Okay, so let me quickly tell you what and all you will learn in a chapter. First and foremost, you will learn something about history of periodic table. Okay, say, can you all tell me how many elements are there in our nature as of now? See, as of now, we have around 120 elements. There are around 120 elements. Okay, but in many of the periodic tables that you find it in your textbook, there were 118 elements, or in some textbook 116 elements. Okay, but as of now there are 120 elements. All of them are not naturally existing. Few are artificially made elements. Okay, so both artificial and natural together we have 120 elements. And when we have to study about these elements, we need to have a particular pattern. Okay, see, scientists have already studied about these elements and they have arranged these elements in the form of beautiful table called periodic table. Okay, so that it's because of this periodic table, study of chemistry has become more comfortable and convenient. Otherwise, you know what, we can't study every element in detailed way, and even when you study you can't remember all of them, right? Say, how is it possible to study every single element in a detailed way? It's not that possible, and it's not convenient also. So we study these elements in group wise. Okay, say there are some elements which look similar, which behave similar, so all of them we study together. Okay, we no need to study every single element. All of them, the elements which are present in one single group, are studied together. We will understand their properties together, because almost all of them will show similar chemical properties. Almost 80% of their properties will match with one another. So all of them we will complete it at one stretch. Okay, so this way we will study the elements of periodic table. So periodic table made the study of chemistry more convenient, I can say, because of this arrangement. Very beautiful, and arrangement follows a particular concept. Okay, so all of that we will discuss in detail. So in a periodic table, like and this periodic table that we are following currently is called modern periodic table. Before this modern periodic table, scientists have introduced many more periodic tables. Almost around 45 periodic tables are there. Okay, so and these periodic tables had one or the other limitation, so we can't follow them. Taking all the good from these periodic table, our modern periodic table was introduced. So to understand modern periodic table, we need to understand something about these periodic tables that were there before our present periodic table. Okay, so we are not studying all the periodic tables which were introduced previously, I mean as a history. we particularly study 4 periodic tables, okay, as history. What we can call it as Genesis. Okay, so Genesis in the sense what? History. So how is our modern periodic table actually came into existence? Before that we were having so many periodic tables, and what were they? And all of them we are not studying. I told you already, right? We are studying only 4 periodic tables. That's important. Okay, so the first one is Dobryner's law of triads. Dobryner's law of triads, and the second one is Newland's law of octaves, and the third one Mendeleev's periodic table, and the fourth one is Lothar Meyer. There is Lothar Meyer periodic table. This will not be mentioned in our textbook, but it's nice to study this periodic table also. So after Newland comes Lothar Meyer's. After that you will have Mendeleev's periodic table, and after studying all the 4 we will go for modern periodic table. And this is one part of a chapter. And about a modern periodic table, we study so many things about modern periodic table. Say how this modern periodic table is classified, on what basis the periodic table is classified, all that we will discuss in detail. And after that we will study something called periodic properties. Periodic properties. We'll try to understand the meaning of the word periodic properties in detail in the later videos. Say under periodic properties, we study about atomic size, ionic size, ionization enthalpy, electronegativity, valency, electropositivity, and many more things. So each and every property we will have to discuss in a detailed way, right? So this is something about the chapter that we are going to study. And in today's video, I am going to complete the entire Genesis, all the 4 periodic tables I'll discuss. Okay, so how these periodic tables were introduced, what were the merits of these periodic tables, what are the demerits, all of that we will discuss in a detailed way. And quickly let us go for the first periodic table, that is Dobryner's periodic table. Okay, Dobryner's law of triads, we say. Okay, and you must understand the meaning of the word triad. Tri in the sense 3. Okay, ADS, it means group. So triads is nothing but group of 3. Group of 3. And during Dobryner's time, almost around 16 elements were discovered. Out of 16 elements, Dobryner could give arrangement for only few elements. Actually, that was the greatest limitation of Dobryner's triads. And let's understand on what basis Dobryner gave his periodic table. It is on the basis of, he arranged the elements on the basis of atomic mass. Atomic mass. Okay, so he arranged the elements in the increasing order of atomic mass, and he followed one principle. He observed one thing in his periodic table, that atomic mass of middle element was the average of atomic masses of first and third. Okay, so this is very, very important. Atomic mass of middle element was the average of first and third elements. Okay, so you will understand once I give his triads. You know what? He mainly gave 3 triads for us. This is triad number 1, this is triad number 2, and this is triad number 3. In the first triad, he arranged lithium, sodium, and potassium. In the second triad, you will find calcium, strontium, barium, chlorine, bromine, iodine. So these are called as, Dobryner's law of triads. Even in your modern periodic table, the first triad is present like this only. I mean, after lithium you will have sodium, after sodium you have potassium. Okay, even calcium, strontium, barium also are arranged in the same pattern, right? So you will find these triads even in our modern periodic table. And see, he arranged these triads in the increasing order of their atomic masses. Atomic mass of lithium is 7. Okay, atomic mass of potassium is 39. Okay, and what he says is the atomic mass of middle element is average of first and last. I mean, if I have to find the sodium's atomic mass, I need to take average atomic mass of lithium and potassium. So what is lithium's atomic mass? 7. What is potassium's atomic mass? 39. 7 plus 39 by 2 if you do, sodium's atomic mass you will get, that is 23. So sodium's atomic mass is 23. Okay, so like that in every triad, the middle element's atomic mass is average of first and last. So this is the main point that you need to remember about Dobrunner's law of triads. Okay, but during his time 16 elements were there, but he could not give justice for all the 16 elements. Based on this principle, he could arrange only these elements in a proper way. Okay, so that was the greatest limitation of Dobrunner's law of triads. So nothing much to discuss about this. Let's quickly go for Newland's law of octaves. Coming to Newland's law of octaves, this is also very simple. Even this periodic table was designed on the basis of increasing atomic mass. On the basis of increasing atomic mass. Okay, so just like Dobrunner, this fellow also followed atomic mass is the property to decide the arrangement of elements. Okay, see, let me first show you his periodic table. See, he started with hydrogen. We know atomic mass of hydrogen is 1. Next element he arranged was lithium. And lithium's atomic mass was 7, right? And after lithium, he arranged for beryllium. After that, boron. Then carbon, nitrogen, oxygen. Then he came back here and he has put fluorine here. Okay, and below lithium he has put sodium. Then comes magnesium, aluminium. Okay, here silicon, here phosphorus, here sulfur. Then he arranged chlorine here. After that potassium, okay, calcium, chromium, titanium, manganese, and he went on like that. Okay, so this is how he arranged the elements based on atomic mass. Atomic mass of hydrogen was 1, lithium is 7, beryllium you will find 9, boron 10, carbon 12, nitrogen 14, oxygen 18, right? So, sorry, oxygen 16. Like that, atomic mass increasing order you will find in his arrangement. And what he also found was every 8th element was similar to the first element. If you consider lithium as the element, okay, first element, then with respect to lithium, which is the 8th element, if this is 1, 2, 3, 4, 5, 6, 7, 8. So with respect to lithium, sodium is 8th element. Like that, with respect to beryllium, which is the 8th element, magnesium. With respect to boron, which is the 8th element, aluminium. With respect to sodium, which is the 8th element, potassium, right? So what he found was every 8th element was similar in the properties. Okay, that means sodium is similar just like lithium. Our potassium behaves in a similar way just like sodium. Like that, he found similarity between a particular first element and its 8th element. Okay, so that is why his periodic table was called as octaves. Octaves in the sense what? Musical notes. So we know the musical notes, right? Sa, ri, ga, ma, pa, da, ni, sa. Indian musical note. See, this is our first note, which is the 8th note again sa. So first note is similar to the 8th note. Just like that, for a particular element, the properties are similar. with eighth element, its eighth element. Okay, so for carbon, which is the eighth element, silicon. With respect to nitrogen, which is the eighth element, phosphorus. So that is why this was called as law of octaves. Okay, so that is important point, guys. So what I can write here, for a particular element, or I can write this way, every eighth element is similar to a particular first element. Okay, so this is the main principle of Newland's law of octaves, I can tell. Fine, everything is fine, and now let us discuss its limitations. So the major limitation is his principle. What is his principle? Every eighth element must be similar to the particular first element, right? His principle holds good only till calcium. Okay, so this principle, I mean, his theory is applicable. It is applicable only till calcium. Okay, you see, with respect to magnesium, calcium, right? Calcium's properties must be similar, that is okay. But you see, chromium, below aluminium, he has placed chromium. But whereas chromium's properties are entirely different from aluminium. Titanium is placed below silicon. Titanium is very much different than silicon. Manganese he has placed below phosphorus, whereas both are very much different. So his theory is applicable only till calcium. Okay, so after calcium, whatever he has arranged, they have actually deviated from this particular principle. They were all having very much different characters compared to the first elements. Okay, so that is the greatest limitation. And the next one is two elements he placed in a single slot. Okay, I mean to say, if you come to this side, I mean first group, so below chlorine or below bromine, he has placed two elements together. Okay, say for example, cobalt and nickel, he placed together. Right, say this is another limitation you can say. So two elements placed in a single slot. Okay, so he could not give any reason why he placed two elements together in one single slot. They should be placed differently, right, in different positions, but they were together. For that he could not give enough justification. And next one is, he did not give any gaps for newly discovered elements. Say during his time, there were around 50 plus elements discovered. He has given place for those 50 plus elements. But what about the newly discovered elements? He could not give any place. He could not provide any gaps in his periodic table for the newly discovered elements. So that is another limitation of Newland's law of octaves. Okay, so this is all about law of octaves. Now we will go for Lothar-Meyer's periodic table. See guys, Lothar-Meyer followed very different method for the arrangement of elements. Actually what he has done is, he has plotted a graph between atomic volume and atomic masses. Okay, so atomic volume is nothing but density. So elements density versus atomic mass. So that is the graph that I have shown it here. See, one thing you can observe is, you see, lithium, sodium, potassium, rubidium, cesium. Okay, let me write it here. Lithium, sodium, potassium, rubidium, cesium. So where are they located in a graph? They are located at the peaks, right? So these guys are actually located at peaks of a graph or a curve, right? So that means all these elements must have had same properties. That's why all of them occupy peaks. isn't it? So he said that yes, these elements belong to one particular group. Okay, you can study them together, because when he has plotted a graph, all of them occupied, peaks, and he called these elements with the name alkali metals. Okay, so all alkali metals occupy the peaks. Say for the competitive question, position of elements can be asked. Say in Lothar-Meyer curve, what was the position for alkali metals? So what was the position here? The position is peak, right? So the peak of the curve is occupied by our alkali metals, right? So this is the first point you have to remember. Now the second point. Okay, let me talk about this. You see beryllium, okay, and this is magnesium, calcium, strontium, and barium. See, they are occupied in a same position. I mean on a descending curve, right? So what is this? The point, you see from here the curve has gone like this, descending. This point and this point you observe, descending position, again this magnesium, descending curve calcium, descending line strontium, descending line barium, right? So the elements which have occupied the descending curve, okay, so elements on descending curve are nothing but alkaline earth elements. Alkaline earth elements. So these elements behave in a similar way. So which are the elements? Beryllium, magnesium, okay, calcium, strontium, and barium. So all of them occupy the descending curve. Okay, I mean the downward curve. And now you see upward curve. Upward curve is what? This one. This is upward curve. Okay. See upward curve fluorine, upward curve chlorine, upward curve bromine, upward curve iodine. Right. So what I will call it as ascending curve. Okay. Elements on ascending curve. Which are the elements? He called these elements as halogens. Okay, so your fluorine, chlorine, bromine, iodine. So all of them have occupied ascending curve. Okay, so all of them must have had same chemical and physical properties. And finally, you see bottom of the curve. Okay, lowest peak is occupied by the transition elements. Okay, the elements which we can call it as metalloids, right? So actually in the modern periodic table you find these elements in between S block and P block, or we can call them as D block elements. Okay, so rest of the elements, P block elements and D block elements, have occupied the bottom peak. So P, or I can say D block. Don't worry about this word, we will study in modern periodic table. So D block elements are found at bottom peak. So what is important to remember is position of elements. So where are alkali metals located? At the peak. Okay, so where are alkaline earth elements located? In the descending curve. Where are halogens located? In the ascending curve. Where are D block elements are located in the curve? At the bottom peak. So position you have to remember here. Okay, so this is how, based on their common position, he could tell that yes, these elements have common properties. That's how one can come to conclusion, right? So that is all about Lothar-Meyer's curve. And you know what, see, only based on a curve we can't decide the similarity of properties between the elements. There are many limitations here. You see here, if you see boron, aluminium, they belong to one group actually in the modern periodic table, whereas lithium and rhodium have very much different properties compared to boron and aluminium. Like all these guys do not show similar properties, in fact, right? So like that, there are many limitations for Lothar-Meyer's periodic classification also. Okay, and now let's go for Mendeleev's periodic table, which is our very much previous periodic table for our modern periodic table. Okay, so many points we can take it, we can find similar between modern periodic table and Mendeleev's periodic table. Let's understand Mendeleev's periodic table in a detailed way. See guys, Mendeleev's periodic table gives very important idea for modern periodic table. See, Mendeleev also arranged all the elements according to atomic mass. Okay, so he also arranged the elements on the basis of atomic mass. And here is a very important sentence that you need to understand. There is something called Mendeleev's periodic law. Okay, so just like modern periodic law, there is a Mendeleev's periodic law. It says that the physical and chemical properties, I'm just writing a short form. Okay, so PHY in the sense physical properties, physical and chemical properties of elements. Okay, that means physical and chemical properties of elements depend on, they are periodic functions of their atomic masses. Okay, so it means that physical and chemical properties depend on atomic masses. Okay, so that means the elements which have same physical and chemical properties gets repeated after certain intervals. I mean after some atomic masses. Okay, say if you have the element number 1 here, say after some atomic masses, again the element with the same physical property gets repeated. Okay, so first element is placed here, then the other element comes here, next element comes here, next element comes here. I mean all these elements which are there in a group must have had same physical and chemical properties. So between this element and this element, there are so many other elements with different atomic masses, right? So that is what the meaning. See, the elements with physical and chemical properties gets repeated continuously after certain atomic masses. Okay, so that's what the meaning of this particular sentence. Fine. And the concept of groups and periods are introduced by our Mendeleev. So he arranged his periodic table in 7 periods and 8 groups. Okay, so you must understand what do you mean by group here. Group is nothing but vertical column. Okay, vertical column is called group, horizontal row is called period. Horizontal rows are periods, vertical columns are groups. So let us just quickly, roughly draw Mendeleev's periodic table. So this is our first group. Okay, so this is a first group, this is our second group, third group, fourth group, fifth group, sixth group, seventh group, okay, and this is our eighth group. Like this, there are 8 groups, 8 vertical columns in Mendeleev's periodic table and 7 horizontal row. Okay, so this is period number 1, period number 2, 3, 4, Okay, 5, 6, 7, like that. So very roughly I am showing you, right? Okay. And now listen carefully. Each and every group is again subdivided into two groups, group A, group B. You see, this is our first group. First group is again subdivided into two subgroups, that is A and B. Like that, our second group is also divided into A and B. Third group is divided into A and B. Fourth also divided into A and B, like that. Fifth also, sixth also, and seventh also. So till 7 groups, each and every group is subdivided into A and B. Okay, so A subgroup, B subgroup in first group, like that. In second group, A subgroup, B subgroup, like that. Till 7 group you have A, B subgroups, whereas 8th group will not have subgroups. Okay, and there are some elements placed in A subgroups. Okay, for example, in the first group, if you come, you have an element hydrogen, lithium, okay, sodium, potassium, rubidium, cesium, right? So very roughly I am showing you. And coming to the B subgroup, you have an element like copper, you know, all D block elements will come here, right? And actually there is no connectivity between A subgroup and B subgroup. Usually the properties of A subgroups are entirely different from the properties of B subgroup. This you keep it in a mind. Okay, so actually this is one of the limitation of Mendeleev's periodic table, I can say. Okay, properties of B subgroup is entirely different, properties of A subgroup is entirely different. But whichever the elements are there in A subgroup, all of them will show same chemical and physical properties. Okay, whichever the elements present in B subgroup, all of them show same chemical and physical properties. Right? So this is how we have 8 groups and 7 periods. And now, once Mendeleev has given the entire periodic table, noble gases were discovered. Okay, so he had to give some place for noble gases. So he introduced the ninth group, that he called it as zero group. So this zero group, in this zero group, you will find the noble gases helium, neon, argon, etc. Okay, so zero group includes our noble gases. Okay, so what actually he did was, he studied each and every element. You know, during his time, almost around 60 elements were discovered. He studied each and every element in a detailed way. You know what? Every element he made it to react with oxygen and hydrogen. Okay, so he conducted reactions of elements with oxygen and hydrogens, with oxygen and hydrogen. Okay, so whichever the elements on reacting with hydrogen, when they have given this particular formula, you know, for hydrides, all of them were placed in the first group. Okay, and when they reacted, when the elements that were placed in the first group, when they reacted with oxygen, they gave the formula M2O type of oxide. Okay, say all these elements, why did he put in group 1? Actually, when they reacted with hydrogen, they gave this kind of hydride, this formula having hydride. And when they reacted with oxygen, they gave this formula, this particular oxide. Okay, and similarly, these guys, when he has placed the elements in the second group, all of them, when they reacted with hydrogen, they gave this kind of hydride. And similarly, when they reacted with oxygen, they gave this kind of oxide. M in the sense what? Any element in group 2. Okay, like that, based on the reactions with hydrogen and oxygen, whatever the product he had got, no, so based on the formula of that product, he arranged the elements into several groups and periods. So whichever the element that has reacted in a similar way with oxygen and hydrogen, all of them he has put in one single group. Okay, so this is a major thing that he had done for introducing his periodic table, right? So all that is very nice. And one more good thing he has done is he left gaps here and there. Okay, for example, you know what, boron, imagine if boron is here, so below boron he left a gap and he called that gap as Eka boron. Eka boron. Okay, like that, you know what, below silicon also he left a gap and he called that gap as Eka silicon. Eka silicon. Similarly, below aluminium also he left a gap and he called with the name Eka aluminium. Okay, actually these are not their real positions. Okay, just for example I'm showing. So below boron he left a gap, below silicon he left a gap, below aluminium he left a gap. Okay, so not only below these elements, you will find gaps in its periodic table frequently, like after few elements. It's because these gaps are because if newly discovered elements are there, they can be placed in the gap according to their properties. Okay, so if the element is showing similar properties with group 1, then in group 1 here and there some gaps are there, so you can place the element in that gap. So depending on what physical and chemical properties are there for a new element, you can give place for newly discovered elements also. So that is the main purpose why he left gaps in the periodic table. Okay, and you know what? See, below boron, he called the element as Eka boron. Eka means what? The meaning of the word Eka means one, okay, or same. It means that this element in this position, you have to place an element which shows similar characters with boron. Okay, so here what do you mean by Eka silicon? There is an element which can be discovered newly and that element shows similar characters with that of silicon. So you have to give the position for that element here below silicon. That's what the meaning of the word Eka silicon. So actually, Eka silicon is nothing but germanium. Okay, so germanium was discovered during that time and people were studying its characteristics. Still, they have not confirmed that it will have similar characters with silicon. But this person predicted that germanium can be similar with silicon. So he gave a place empty below silicon and he called that germanium as Eka silicon. Still, name was not given for germanium. Okay, but he predicted, Mendeleev predicted that it can be similar with silicon, so he left a gap below silicon and called germanium as Eka silicon. Okay, similarly, Eka aluminium is nothing but gallium. Okay, so gallium was also discovered during his time and still name was not given, and he predicted that gallium can be similar with aluminium, so it has to be placed below aluminium. So still name was not given, right? So he called that gallium as Eka aluminium. Eka means what? Same or one, similar. Okay. So that's what about the gaps that he left in his periodic table. So this is a very good thing that Mendeleev had done, if any new elements were discovered in the future. So all this is about Mendeleev's periodic table. And now let us study about the limitations of Mendeleev's periodic table. These limitations are very, very important to understand. See, the very first limitation that I will be discussing is about the position of hydrogen. So what I can say is position of hydrogen is uncertain. hydrogen is uncertain. Uncertain in the sense what? Doubtful. Okay, so he could not confirm the position of hydrogen. Actually, I have written hydrogen here, but in his original periodic table you don't find hydrogen here, because there is a controversy in deciding the position of hydrogen, because hydrogen shows similarities with alkali elements like lithium, sodium, potassium, rubidium. They are called as alkali elements. Hydrogen shows similarities with alkali elements, and it can also show similarities with halogens. Halogens are nothing but fluorine, chlorine, bromine and iodine. Okay, so he was in a confusion that where to place hydrogen, whether to place it with alkali metals or to place it with halogens. So this was a big doubt. So that is the reason he could not give justice for the position of hydrogen. So that's why we say the first limitation as the position of hydrogen is doubtful, that is uncertain. Okay. And the second one is very importantly, no position. He did not give any position for isotopes. So we all know what do you mean by isotopes, right? Isotopes are nothing but elements, okay, atoms of same element, they have same atomic number but different atomic mass. See, carbon 612, carbon 613, carbon 614, like that. Okay, so isotopes are actually atoms of same element. Atomic number is same, atomic mass is different. This guy has arranged the elements according to increasing order of atomic mass. Say if he arranged lithium here, he has arranged beryllium here, boron here. So after that like that, in the increasing order of atomic mass, he has arranged all elements. That means if he has arranged carbon 12 here, carbon 13 must come here, no? Carbon 14 must come here, because atomic mass of carbon 12 is 12. Atomic mass of this carbon is 13. Atomic mass of this carbon is 14. So almost every element has isotope. Okay, so if you come to nitrogen, nitrogen 14 is there, nitrogen 15 is there, nitrogen with atomic mass 14, nitrogen with atomic mass 15. Okay, like that. If you come to oxygen, oxygen 16 is there, oxygen 18 is there, right? So every element has isotopes. So the isotopes also must be placed when he considered atomic mass, because isotopes will have different atomic mass with same atomic number, right? But he did not mention isotopes of any element in his periodic table. When he considered atomic mass, he must have mentioned isotopes also, but he did not mention any isotopes, right? So that is another greatest limitation. And coming to the third point, okay, you will find somewhere that tellurium is placed after that iodine is placed. Actually, tellurium's atomic mass is 127.6. Iodine's atomic mass is 126.9. You see, iodine should come here, tellurium must go there, right? So element with higher atomic masses are placed before than the elements with lower atomic masses. Okay, so yes, here and there some misplacements you can observe, right? So that is another limitation of Mendeleev's periodic table. So most of the cases you will find this kind of pairs everywhere. I mean, like every situation in the periodic table. Okay, so one such example I have mentioned here. Actually, tellurium must come here because it has a higher atomic mass. But tellurium is placed first, later iodine, right? So this kind of situations also you will find in this periodic table, right? So this is all about Mendeleev's periodic table. Okay, so you must know on what basis Mendeleev has given his periodic table. It is based on atomic mass. And very famous sentence, you should not forget that. What is that? Physical and chemical properties are periodic functions of their atomic masses. Okay, and the concept of group and period is also introduced by Mendeleev, and that is what used later to introduce modern periodic table. Even in our modern periodic table, we say there are 18 groups and 7 periods, right? So concept of group and period has come from Mendeleev only, right? And the way he left the gaps for newly discovered element is one interesting fact what modern people thought. Okay, so and even modern periodic table, you can give place for newly introduced elements, right? So that's what about Mendeleev's periodic table. So this completes our history part of what is that periodic table. And in the next class, I will talk about the modern periodic table in a detailed way. I'll be finishing modern periodic table overview, as well as the different classifications that are there in our NCERT textbook about modern periodic table. Okay, so let's revise the concept. And do subscribe our channel to learn the concepts in the easiest way and in a detailed way. And don't forget to share the videos with your friends. Let everybody get benefit out of this. Thank you so much. I'll meet you up in the next class.